Okay, thank you for the introduction. Thank you all for being here. So, hackers can guess pins using your smartphone sensor data. We see more and more articles like this in the press, in the internet. This reinforces the idea of how important is hardware security nowadays. Today I bring you crucial concepts on how this securing of the hardware should be done, and also I bring you how to do this, how to secure hardware with lower latency. This is the outline of my presentation. It is divided in two main points. First, I'll talk about this concept of the important concept to secure the hardware, which will be the input dependencies. And then in the second part of the talk, I'll talk about how to lower the latency of these secure implementations. So, present a bit of a couple of masking schemes. We used threshold implementations, also known as TI. This is the first sharing scheme we use in our work. This is first order 2-bit AND gate, first order secure protection. TI, the input shares defined on TI come in function of the algebraic degree T of the function and the degree of security you want to achieve. A key property of TI is the 10th order non-completeness, which is referred a lot in our paper. It is defined as follows. Every combination of T output shares should be independent, must be independent of at least one input share. In this example of first order, we see that every output depends only in 2 input shares. The second sharing scheme we use in our work is domain-oriented masking, also known as DOM. Now they reduce the input number of shares to T+1, which is only depending on the degree of security. So for first order, we see here the 4 cross products, followed by a layer of a refreshing layer, a synchronization layer, and a compression layer to go back to 2 shares. It's important to see that now we need a layer of registers to secure this multiplier. So, DOM multiplier needs an extra condition, which is input dependency. It needs that both inputs are independent of each other. What this means, given our multiplier, first order multiplier, we have here our 4 cross products. The dangerous one are these 2, which mix 2 different shares. Now, 2 different shares of 2 different variables, which are independent between them. So it is non-completeness. It's okay now. What happens when they are dependent? Let's check another example. Calculating x cubed. We first perform the square, x squared, which results in both shares like this, and then x by x2 to obtain x cubed, sorry. We see like this, where these 2 cross products are failing non-completeness. So this is the danger of dependent inputs. Here it's pretty simple, it's quite obvious, but there are other cases where it is not that obvious. For example, in Keccak, we have this first permutation theta introducing these intricate dependencies, which later on in the nonlinear operation might become dangerous. This is dangerous for round-based implementation, since all the permutations go one after another. In a sequential implementation, we would use registers in the middle, so dependencies would be broken. We find a non-completeness leakage, a non-completeness flaw in a round-based implementation of Gross et al., where they use a DOM multiplier, DOM sharing scheme to protect. This could lead to a potential exploitable leakage. So now show you how do we, well, this is the implementation of this DOM sharing scheme, where we see, we see how all permutations are calculated one after another. Here we see the refreshing layer, the register, and the compression layer. But there is a non-completeness failure in G. How this failure comes? How is this produced? So I'll show you an example of one bit failing this non-completeness. This bit is a bit of the third cross term in bit 410. So this is the operation, the G step, which makes this output bit depending on these two inputs of two different shares, which initially are two different variables. Now let's see what are the dependencies of these variables. The previous step is B step, which just move the bits in the plane. Then it's followed by, well, previous step is row, which moves the bits along the z-axis. These are okay, just moving bits around. Now it comes theta, which creates all these dependencies. So now we can see that this bit 304 and this here 304 in share 1 and 2 are used. So this bit depends on these two bits, 304 for share 1 and share 4, share 1 and share 2 failing non-completeness. How do we fix that? Well, first we did an evaluation of this implementation. We implemented ourselves to make sure the comparison was done as fair as possible. We see when masks are off, the countermeasure is switched off, we see huge leakage. When masks are on, we still see small leakage in the first order. We do this test with the test vector leakage assessment with 55 million traces. Now we propose our fix, which is pretty easy once the problem is spotted, right? Which was the tricky part. We just add a new register in the middle, breaking the dependencies produced by this theta permutation. We can make this better. We can reduce the number of registers by moving this up before the state register, so we merge these two registers. Well, this here, non-completeness is correctly fulfilled. This is the more optimal design with less layers of registers and with non-completeness still fulfilled. We also do an implementation, evaluation of this implementation. Now I just present the first order and second order t-test, t-test over the implementation. So for the first order we see first order no leakage, second order and third order yes, second order no leakage for the second order implementation, leakage in the third order for the same conditions. Now the second part of my talk, I'll explain how do we lower the latency of these checker implementations. So what's the aim? We want to halve the number of cycles our implementation takes to finish. To illustrate our methodology, I'll present a very small example of a 4-input AND gate, which we split into two layers of quadratic operations. So we apply a first order sharing scheme to both layers with 3 shares and with 3 shares for both layers. We see these are the input dependencies on the output of the first layer. When applying the AND gate, when applying the second, the quadratic operation of the second layer, we will get with the combinations in the output, all of them will fail non-completeness. So how we solve this? We apply a second order sharing scheme in the first layer and a first order sharing scheme in the second layer. So when the second layer operation is applied, we are sure that all the combinations preserve this non-completeness. So this, due to the algebraic degree 2 of the AND gate, we see that the outputs of the first order, the outputs of the first layer needs twice order protection than the outputs of the second layer. So this leads us to a general formula applicable to any scheme and to any order. So this is a recursive formula given target order of protection. We crawl back, calculating the protection orders for the next layers by multiplying the degree of security of the next layer and by the algebraic degree of the next layer. This is only with this we don't specify the sharing scheme to be used, but only the order that should be used in every layer. The refreshing for multivariate security is not specified either, and this might not be the more optimal sharing scheme to use, but it's a starting point towards lower latency masking. So now, how do we apply this to Keccak? This is what we want, to compute 2 rounds at once with no registers in the middle. So as we've seen at the beginning, DOM kind of masking schemes need registers to avoid linear dependencies and to avoid input dependencies. So we use TI. First layer needs, well, we target first order security. First layer, we will use a first order sharing scheme. Second layer, we will use a second order sharing scheme as presented before. We have first option following the straightforward equations from TI. First sharing scheme, the second order, 5 input shares, 10 output shares. Second layer, input shares, 10, coming from the previous output. And we do a compression sharing to go back to 5 shares. So a 10 to 5 sharing scheme for first order, that's much more than normally needed, right? Second option, we try to find a more optimal way. We use 2 6 to 6 sharing schemes. So now I'll present a bit more in detail the 6 to 6 sharing scheme. If you, I invite you to read the paper to see more details on the other one. These are the dependencies on the first layer. First output share, every output share depends on 3 input shares. And then on the second layer, same thing, every output share depends on 3 input shares from the previous layer. This, if you substitute the output share here with the inputs, we see that every output share of the last layer is missing always at least 1 input share on the inputs. Well, in this case, exactly 1 input share. We evaluate the 6 to 6 sharing scheme, and these are the results. With masks off, we see huge leakage. With masks on, we don't see leakage anywhere. Taking into account that we are operating on 6 shares, that's a lot of noise, so that's why we don't see leakage in the second, neither the third order. These are the numbers for our implementations. We take nine clock cycles. Well, first of all, we are comparing previous works were done using Keccak. 1600 bits for the state. We use 200, which it doesn't matter for the number of clock cycles. Maybe yes for the maximum frequency, and obviously yes for the area. We get big area compared to previous works, but we see we've reduced the number of clock cycles drastically. The maximum frequency is also lower, but with with how much we reduce the number of clock cycles, our implementation is still faster than previous works. As a conclusion, I bring you a wrap-up of our contributions. We discovered a flaw in previous round-based Keccak secure implementations. We analyzed the problem and give a solution to it in order to prevent future implementations to fall in this problem. And then we present a methodology on how to lower the latency in these secure implementations. We apply this methodology to speed up Keccak implementations. Thank you so much for your attention. I'll be happy to answer any question.